on text analytics at IBM. At this point in time, we're beginning to explore using Spark to perform text analytics. Before we begin with an integration, I just wanted to show this for a second, quick second, move on. So we'll start with explaining why we brought about text analytics, the sort of engine that we have, the sort of ecosystem that we've got, and what it does compared to what our experiences have been in the past. I'll then go over some of the internals of our system. I'm not sure how many of you have been exposed to text analytics from our group. Before we discuss how we've integrated text analytics in a Spark ecosystem. So when we began IBM research, they ran into a problem with information extraction system where their expectation was that such a system had to be expressive, efficient, transparent, and usable. They ran into systems that were pretty much rule-based in the sense that they were leveraging cascading grammars, which had efficiency issues, and also black box solutions, which were using a lot of learning under the cover, and it was very difficult to be transparent and to identify problems in extractions. We then came up with a theoretical and then a very practical solution of a declarative information extraction system that did perform a lot of cost-based optimizations under the cover. The runtime that we ship with this is very high performant, and we also have a lot of extensive developer tooling around it. In our system, we've got the notion of developers writing information extraction routines. These are written in a language called annotation query language, AQL. This is a very trivial extractor that we write. An extractor is an information extraction routine. As you can see, this is very English-like, very easy to read, and it is very SQL-like as well. So in this small snippet, we're just trying to identify the intent to buy across a certain set of products. This extractor then gets compiled into a bunch of execution plans that our optimizer uses a lot of optimization strategies under the cover to pick the most optimal one from these from the sample space, and then it feeds it through an efficient runtime, which basically looks at one document at a time. So you're effectively doing local analysis where you're applying the chosen execution plan on top of a document, and you're getting the extractions that you're after. So this is a little bit about each one of the components. There have been numerous publications that have all disclosed the internals of these systems for more reference. And we do expose AQL language out of 2 IBM products, and we ship the system T runtime with more than 8 other products from IBM. And a little bit about the runtime. As I said, we compile the extractor. The optimizer picks the best execution plan. It uses a few optimization strategies, one of which is rewriting AQL rules itself. Another is once you created a global execution plan, you also rewrite that plan again if you want a better execution. And we do a lot of cost-based optimizations when we get to the point of executing that plan. Things like conditional evaluation, where we don't evaluate parts of the plan if we don't necessarily get any output from them looking at the document. So as far as information extraction itself goes using our platform, first we've got the low-level constructs of our AQL language, which are then used by us to build a lot of extractors or extractor routines. So in this case, we have named entities, log data or machine data extractions, and then we also have a bunch of financial extractors. We then also look towards wrapping around dependency parsers, providing normalization of noisy data, and we also expose all these extraction routines for more high-level extraction pipelines to be performed, which are more domain-specific. For example, log extraction, then health sciences, piracy extraction. We've done numerous interesting use cases around this. So this is again a slightly more non-trivial snippet. It looks pretty easy to read, but then it does involve a lot of complicated things in the background. We let you import objects from other routines. We do work with dictionaries and regular expressions, of course. And then we do all the fancy stuff that we do in relational algebra. All of these objects within AQL are combined using relational operators for us to get the final extraction outcomes. So in this case, think of actions as verb classes, roles as subjects and object. We have more formal names in our API documentation. Finally, this is a slide where we would like to demonstrate how System T performs with a well-known open source information extraction system out there, which is GATE, General Architecture for Text Engineering. They have something called ANI within them, which is a comparative information extraction system. They even have an optimized version of ANI with onto-text transducer. So we ran our person information extraction against their person information extraction routines, and these are the numbers that we got as far as precision, recall, and F measures go. These were the data sets we used, Enron, WebCrawl, and then Finance. We also then performed a lot of throughput and memory evaluations against these two runtimes, and we found System T to be very much better than whatever we compared with.
So now that we've seen the power of AQL, I'll talk about the tools which enable developers to write these information extractors. So first, what I have here is a screenshot of our Eclipse tooling, where you have a nice extraction flow. You go through the steps of importing the documents that you're looking to extract information, and then write AQL, in the AQL editor to run and execute the AQL that you've written. So you see, you can, select the document selections here from a list of documents, and then here is the AQL editor where you write your AQL. And we also have in the extraction plan, so the extraction plan is nothing but the design view of the pattern that you're building. So in this example, for example, we have some fourth quarter revenue earnings documents where you're looking to extract the revenue for certain divisions in IBM. So you would start to write the AQL for that pattern here. Once you've written your AQL and executed it, you can view the results. You can view the results in a very structured manner. So you can see we have the different columns of the extractor exposed here. You have, for the person extractor, you have the first name, last name, and middle name, along with the spans. And also, you can nicely view the results highlighted in your document for the specific extractor. So the Eclipse tooling is very useful for developers who want to learn AQL, write AQL. Now there's a certain another group of users who probably say, okay, I still want to do my information extraction, but not learn AQL. So you can still develop these extractors, but visually and graphically. So this is not there yet in a future release, where you're going to be exposing at least 80% of the expressivity of AQL. So here, we have the list of the pre-built extractors, like the named entity extractors, the financial extractors, the machine data accelerators. And you can define, new extractors like dictionary, regular expressions as well. And you can quickly build a pattern together, just, using drag and drop. So you can drag, any of these pre-built extractors from the catalog to the canvas, create new ones, and, and then build your pattern and execute it. So in here, this is just a quick example of a pattern that shows you we are trying to extract suspicious IP addresses from a set of system logs. So just like you saw in the Eclipse tooling, we highlight the results in the document viewer, and we would also show the results in the output grid. So to sum it up, the life cycle of a text analytics application, from a developer's perspective, you're going to start with your input data. Now, your input data, probably would be large. So when you start with it, you're going to try to create a subset of it. And you're going to use sampling to create a subset of this data so you can download it, towards your local workstation. And we have, our Big Insights web console, which has this feature. Once you have a subset of the local data, then you're going to either use the Eclipse or the web tooling to develop these extractors. So this whole process is very iterative. You develop your extractors, you execute them, view the results, and then refine your extractors further. So it's a very iterative process. And then once you are satisfied with your extractors, you would publish it as an application. So again, today from the Eclipse tooling, and we'll have that in the web tooling also, you will be able to publish your extractors to an application. And you could take that application that you've generated and deploy it. And we do have that capability in the Big Insights console today. So once you have that application, what do you do with that? And now that you want to run it against your massive data set in your cluster, so we have various options. You could write a Java MapReduce program to do that. Spark and the Hive UDTF is what I'll talk about. That's are part of our exploration work. We also expose our extractors as a UDF in Pig. And Jackal is another way to execute these extractors in MapReduce. So this is kind of just summarizing the steps we just talked about. Sample your data, develop your extractors, publish it as an application. Once you deploy the application, then you can run it as a distributed job, and you can visualize and iterate. So now we'll quickly talk about the integration work that we have started on. So we tried out two routes. One is the Spark and Java application, and the other is a Hive UDTF that we will invoke from Shark. So the process is, we read the data from HDFS into Java RDD, and then we would run it as a MapReduce using the map function that we have in Spark. And what we're doing there is invoking the system-T APIs. So we're transforming each entry into from the RDD into a record that system-T understands. We're using the operator graphs and applying this to the input tuple, and then finally gathering the results and returning it to the caller. So we get the results, and we store it back into HDFS. So similarly for the Shark UDTF, we are reading now the data from HDFS into a table and invoking the normal Hive query, and going through the same system-T APIs and saving the results into a table. So this is I guess the initial exploration via the Hive UDTF, but I guess going forward we'll also explore the Spark SQL. So since we couldn't get the browser on the other tablet working, I'll show the screenshots of the application that we've tried out. But going forward, what we plan to do is, of course, stress test our current integration with massive data sets and much more complex extractors. I mean, so far we've tried out the named entity extraction. Maybe also integrate the developer tools that you saw, the upcoming web-based with the Spark-based IBM text analytics, and explore even text analytics as a feature extraction component within machine learning pipelines. And the last one is possibly exposing the text analytics to Scala developers. So here are some links to references for the research publications, the product documentation, and also the reference documentation on AQL. And we'd like to invite you, we leave you with, if you want to also do massive data scale analytics, open source, RDD, Spark, efficient query languages, AQL, come talk to us after the talk. So I just wanted to quickly share the screenshots of our simple application that we tried out, which is for the named entity extraction. These are some of the details, and this actually shows the results of the extraction that we extracted and stored it on HDFS. That's it. that's about it.
Questions? Now we gotta use the microphone for the cameras.
Can you compare and contrast with UEMA, which also came out of IBM?
I'm sorry, could you repeat that?
UEMA, can you
Sure.
compare the two?
Sure. So UEMA is a larger pipeline. So within a UEMA framework, you would have systemd run as an annotator. So you would expose systemd as an annotator within UEMA. So typically, any named entity extraction here will sit inside an annotator, and that will be run within a UEMA pipeline. And we do offer support for UEMA from within systemd.
Hi. Do you provide the sentiment analysis functionalities too?
On, sorry?
Sentiment.
Sentiment analysis integrated functions.
Sure.
So the short answer is yes.
Yes, yeah.
But we just wanted to get back to the slide where we actually had the AQL for the action API, or we didn't talk about the action API.
So the box that says social, log, and email information extraction includes sentiment, intent, buzz, so on.
All right, last question.
Is any of this open source yet?
This isn't open source yet.
All right, thanks again.
Thank you.
Okay, thank you.
So we are at our first break of the afternoon, and we are back on time. We will see you at 3 p.m. in a half hour.